Alright, now let's talk about local counterfactual explanations. As machine learning models are being increasingly deployed to make high stakes decisions, it also becomes important to provide recourses to affected individuals. And this is exactly what counterfactual explanations will help us do. So, counterfactual explanations give us the following information. They tell us what features need to be changed and by how much to flip a model's prediction. That is, to reverse an unfavorable outcome. To understand this better, let us consider a concrete application scenario where an applicant sends his loan application to a bank, and the bank might be using a predictive model, in this case f of x, to determine which loan applications should be approved and which ones should not. In this particular case, let us consider the scenario where this particular applicant's loan application is rejected by this predictive model. Now, instead of just communicating this rejection decision as it is without any other input, it can be extremely useful to the applicant if we provide more information about what he can change in order to increase the chance of his application getting accepted the next time he applies for a loan. So, what we design or what we think of is to basically have these counterfactual generation algorithms which communicate with the predictive models and provide recourses to the end users. For example, in this case, a recourse might look like increase your salary by 50K and pay your credit card bills on time for the next 3 months to increase your chances of getting your loan application accepted. Okay. All right. Now let's talk a little bit about the intuitions behind how to generate counterfactual explanations. What you see here is basically a simple diagram showing a decision boundary between the positive and the negative classes. Okay. We have an instance X for which we need to find the counterfactual. And the intuitive way in which several algorithms try to do this is by basically making small modifications to X until X crosses the decision boundary, or this new version of X crosses the decision boundary and its prediction flips. Okay? Such instance is called as the counterfactual of X. So in this case, you see 2 points, CF1 and CF2, which are both counterfactuals of X. Okay? And CF1 is obtained by moving X in the direction A, and CF2 is obtained by moving X in the direction B. And as you notice, both CF1 and CF2 are on the positive side of the decision boundary. So both of them are actually valid counterfactuals of X. Okay. A lot of the different algorithms designed to generate counterfactual explanations pretty much differ on 2 key questions. One is how to choose among the various possible candidate counterfactuals, and the second is how much access is needed to the underlying predictive model when we are trying to determine what the counterfactual would look like. Okay. All right, now let's go and look at some of the most important algorithms which were designed to generate counterfactual explanations. The first algorithm for this problem was proposed by Wachter et al., and they use the simple objective function where the goal is to find a counterfactual x prime for a given instance x in such a way that f of x prime, that is the predictive model's prediction on x prime, is actually the desired outcome, and the distance between x and x prime is as small as it can get. Okay, so that was their high level idea of what the objective function would look like. Okay, and as you can see here, the distance metric is a key component of this objective, and the choice of the distance metric dictates what kinds of counterfactuals will actually end up being chosen. And Wachter et al. Employed a normalized Manhattan distance as their distance metric. All right. So, in fact, Wachter et al. Used a slightly different version of this objective that we just discussed, which is shown on the right-hand side of the slide. This version of the objective is actually unconstrained, as you can see, and is also differentiable. And they use Adam optimization algorithm with random restarts to solve this objective. So one of the key points to note here is that Wachter et al.'s algorithm requires access to gradients of the underlying predictive model, so it is not dealing with a complete black box. All right, so these are some of the counterfactuals output by Wachter et al.'s algorithm. As you can see, in case of person 1, the counterfactual says that if the LSAT score was 34, then a person would have obtained a desired score, right? And then other things to pay attention to here involve persons 3 and 4. What you actually see is that the counterfactual is asking these people to change their race in order to obtain a desired outcome. And as we all know, it is impossible to act upon these features. Now, how to fix this problem and how to generate counterfactuals which are actually more feasible, that is our next part of the discussion. In fact, Houston et al. Exactly deal with this problem. They rethink the objective function that we saw earlier a bit more, and instead of thinking about minimizing the distance between x and x prime, they take a different approach. They basically introduce two new pieces in the objective function. One is, instead of the distance between x and x prime, they actually consider the cost that one needs to incur to change from x to x prime. Okay? And they try to minimize that particular cost. And also, if you notice, there is another variable introduced, which is A. A is basically the set of feasible counterfactuals input by the end user. For example, end users can explicitly say that changes to features like race and gender are not feasible, therefore they cannot be valid counterfactuals. Okay? And the cost function that is chosen by Houston et al.'s work is actually total log percentile shift, and they use this cost function to capture the fact that changes become harder when starting off from a higher percentile value. That it is harder to move from 90th percentile to 95th percentile than it is to move from 50th percentile to 55th percentile. So this logic is captured in the log percentile shift, which they use as their cost function. Okay. Houston et al. Only consider the case where the underlying model is a linear classifier when solving this problem. Okay, and that, as we all know, can be somewhat limiting. Furthermore, their approach actually requires complete access to the linear classifier, which means they need to know the weight vector of the linear classifier. So their approach is not designed to work with black box models. Now, one might ask a question, what if we have a black box or a nonlinear classifier as our underlying model? In that case, there may be a workaround. First, we could generate a local linear model approximation, for example, using an approach like LIME, and then apply Houston et al.'s framework on top of it to come up with these counterfactuals. Here is an example of a counterfactual produced for a particular loan applicant using the approach of Houston et al. As you can see, there are different kinds of changes being recommended to reduce the number of credit cards from 5 to 3, and also to reduce the current debt from $3,250 to $1,000. One thing I would like to point out here is that in this particular context, when we think of the current debt changing, it could also potentially affect other features. And in fact, in a lot of real world settings, changing one feature without affecting another is almost impossible. So how would this really affect counterfactuals, or would it affect at all? To understand, let us again consider this scenario and study this more deeply. Okay? Now, we gave this loan applicant a recourse which asked him to reduce his current debt from $3,250 to $1,000. Let's say this applicant comes back after an year and says, hey, my current debt has gone down to $1,000, now please give me a loan. But then the predictive model might say that, well, that is true, but your age has also increased by 1 year and the recourse is therefore no longer valid. Sorry. Right? So these kinds of scenarios can definitely occur in practice. So it is extremely important to account for feature interactions when generating counterfactuals. But how do we actually do it? That will be the topic that we discuss now. Mahajan et al. And Karimi et al. Propose some solutions to tackle this problem. For example, Mahajan et al. Propose a new variant of the objective function where instead of the standard distance metric d that we were looking at or using so far, they actually consider a new distance metric denoted by d underscore causal, which leverages the structural causal model in the entire process of generating counterfactuals. To try and understand this metric a little better and to develop an intuition for it, let us consider this example where we have a data set with three features, feature 1, 2, and 3, and what you see on the screen is a causal graph of that data set. What we see here is that feature 3 has two parents, feature 1 and feature 2, and neither feature 1 nor feature 2 actually have any parents in the causal graph. So their approach divides all features into two groups, a group U, which is basically the set of those features or nodes with no parents in the causal graph, and a set V, which is basically the set of those features or nodes with at least one parent in the causal graph. And using this definition, they define this new distance metric, where for each feature U for which there is no parent in the causal graph, they essentially use the same old standard L1 or L2 distance between the corresponding feature values of the original instance and the counterfactual. That is, they compute the distance between XU and XU prime. Okay. On the other hand, for those features V, which basically have at least one parent in the causal graph, they compute the distance between xv and the expected value of x prime v given the values of the parents of this particular feature v. Okay. In doing so, they are essentially incorporating the causal structure of the graph into the process of counterfactual generation, which means they're also incorporating the interactions between the features or considering them when generating counterfactuals so that the problems like the ones we just saw do not arise, right? Okay. So their approach, of course, requires knowledge of the full causal graph, which can often be impossible to obtain in practice. But empirically, they show that partial knowledge of the causal graph also seems to work fine. In addition, they propose a workaround where end users can provide inputs about feasibility constraints and the partial causal graph. And in order to solve the proposed objective, they leverage a variational autoencoder. And one thing to note here is that their approach requires access to gradients of the underlying predictive model. Now, other notions of feasible counterfactuals have also been proposed in literature. For example, one notion is based on the idea of data manifold closeness, where the goal is to generate a counterfactual which is actually close to the original data distribution. This basically uses the intuition that counterfactuals which are actually very far off from the original data distribution may not even be valid data points. And another take on what a feasible counterfactual should look like enforces the notion of sparsity by ensuring that we only change a small number of features in the counterfactual, because requiring a user to act upon a large number of features can often be extremely hard in practice. All right, now we are going to talk about the next type of explanations, that is global explanations. Global explanations are designed with the goal of explaining the complete behavior of a given model, which could potentially be a black box. So these kinds of explanations provide a bird's eye view of model behavior. And these explanations help detect big picture model biases which are persistent across larger subgroups of population and which are often harder to detect by examining local explanations of several instances. In that sense, global explanations are actually complementary to local explanations. Just to rejog your memory, while local explanations try to explain the individual predictions of a given model, global explanations try to focus on explaining the complete behavior of the model. And while local explanations help unearth biases in the local vicinity of a given instance, global explanations help shed light on big picture biases which affect larger subgroups in the population. And while local explanations help us vet if individual predictions are being made for the right reasons, global explanations help us vet if a model at a high level is suitable for deployment. Now let's jump into some of the techniques which are proposed in literature to construct global explanations. Let's start with the first approach where a global explanation is seen as a collection of local explanations. All right, the idea here is to basically first generate a local explanation for every instance in the data using one of the approaches that we discussed earlier in this talk. And once we have that, we then pick a subset of k local explanations to constitute the global explanation. And the choices that we really need to make here are what local explanation technique to use and how to choose the subset of k local explanations. Now let's see one of the first algorithms which actually uses this kind of idea or intuition. The algorithm is SP-LINE and it tries to construct global explanations using local feature importances. By now we are all aware that line explains a single prediction or local behavior of a model for a single instance, right? So in this case, this black dot corresponds to a single explanation. And it is quite impossible and extremely hard to examine all possible explanations to understand the global behavior of the model. So instead, SP-LINE advocates to pick k explanations to show to the user. And how can we pick these k explanations? These k explanations are picked in such a way that they're representative, that is, these explanations summarize the model's global behavior, and they're also not redundant and diverse. So let me explain a bit when I say what I mean by not redundant or diverse. Now let's consider the three dots that you see on the slide here. The red dot, black dot, and blue dot, each of these correspond to an explanation. Let's say that we have already picked the explanation corresponding to the black dot into our subset of k local explanations. Once the black dot is picked as one of the explanations, adding the red dot explanation to this set of k local explanations is not going to add much value. In fact, it would be redundant because both the explanations corresponding to black dot and red dot are describing the same decision boundary roughly. On the other hand, if we choose the explanation corresponding to the blue dot, that is not redundant and that provides diversity because it's capturing a different decision boundary. Now, SP-LINE formulates this intuition as a submodular optimization problem and greedily picks a subset of k local explanations. And as we can see, this procedure is model agnostic because it does not require access to the internal details of the underlying predictive model. Now, if we repeat the same procedure but replace line using Anchor's algorithm, we will obtain a global explanation which is a subset of k local rule sets because Anchor's algorithm actually outputs local rule sets. And even this algorithm that is called as SP Anchor is going to be model agnostic.